Okay, guys, so this is lesson number 2, and we will be covering the following objectives. Excuse me, sorry. We will be covering this one and this one right here. So you are going to recognize various techniques that can be used to separate matter, and we talked about physical separation and chemical separation of matter. And you will also classify changes in matter as either physical or chemical and give examples of each. We have completed objective number 1 and objective number 2 in lesson number 1, previously recorded. Okay, so let's begin on page 5 in your note packets, physical versus chemical changes. So matter is always changing. Ice in your drink melts, wood in your fire burns. A physical change is a change that does not alter the chemical properties of a substance. An example would be cutting paper, because this is not actually altering the substance. You're just cutting it into different tiny little pieces. Another example would be a phase change. So from solid to liquid and liquid to a solid, which would be like freezing, obviously. Okay, so I'm going to stick this in here. Phase change. A change in size or shape, so cutting paper. As well as saying that we have the same material but a different form. And I'm going to abbreviate different. Okay, different form. It looks different, but it can go back to the original state. Okay, so you can actually reverse the change. All right, so if we cut paper, we can actually reverse it and basically tape it back together. Phase change, if we melt an ice cube, we can actually take that liquid water, freeze it again, and it will become an ice cube again. Sorry about that. We'll delete that. Okay. And so there will be no energy as a product. Okay, so it looks different but can go back to the original state. No energy is formed as a product. An example of physical change, as we can see here, is melting ice. This is reversible, and therefore it is a physical change. Okay, next page, or bottom of the page. Chemical change is a reaction in which the composition of a substance is changed. So, for example, rusting. And I talked about this in class, about your bicycle, leaving it outside. Okay, rusting will occur over time because of the exposure to oxygen in the air. Water will speed up this process, but it does not actually cause the rust. It's the oxygen that causes the rust. Properties are not the same as the matter. Energy is produced during a chemical change. And this is generally in the form of light, fire, heat, etc. So here we have firewood burning. And what do you get? You get ash and heat, as well as some fire. Okay, so let's look at some examples here. We have change of matter, burning toast. Would that be a physical or a chemical change? Well, we have to think. Burning, we looked at this example up here. Okay, and when you burn toast, you end up with that ashy stuff on your burnt toast. All right, so that is going to be a chemical change. Making ice cubes. Is it reversible? Yes. Therefore, it is physical. Burning a candle. Well, this is a tricky one because you can kind of reverse the melting wax. Melting wax would be a physical change, but if we're burning something, sorry about that, if we are burning something, then it would be a chemical change because you actually see that black smoke while the candle is burning. That is a product. It is also producing a little bit of heat, so that's going to be a chemical change. Spoiling milk. Do you have a new substance when milk goes bad? Yes, you do. So it will be a chemical change. It's not reversible. Once the milk has gone bad, that's it. You're going to throw it away. You can't actually do anything to it to make it become good again. Making Jell-O, we're going to say, is a physical change. Okay? Because actually, if you add water to the Jell-O, you're actually going backwards into the process. So we will say that it is a physical change. All right, going on. So let's go to page 6. Elements versus compounds. So number 1 says circle all of the elements and underline the compounds below. So we'll do this together. On the lines, we're going to record the number of different symbols within the species. So we call all of these things here species. Okay? Well, we have a C and an O. If you look at your periodic table and your reference tables, you'll see 2 symbols here. So we are going to underline this because this is a compound. So we're going to actually start with just doing number 1. This is a compound. You see 2 or more symbols. Compound, 2 or more symbols. This would be an element. And remember Brinkelhoff, oxygen is in there. So again, when it's by itself, it's got to be diatomic. C by itself is an element. Mg, which is magnesium, by itself is an element. Here would be a compound. Helium, by itself is a compound. Water is a molecule or a compound, 2 or more elements. Copper is an element. Cobalt is an element. We're going to talk about the rules for symbols. Chlorine, element. Brinkelhoff, Cl falls under the Brinkelhoff, so diatomic by itself. Ni3 is, whoops, sorry about that. Going too fast. This is a compound. All right, so we're going to underline this. Let's fix this up here. NaCl we talked about in class. Table salt is a compound, and iodine is an element. So let's go back on the lines provided. Record the number of different symbols. There are 2 here. We have cobalt, or carbon, and oxygen. Here we have 1, 2, 3. Okay, we don't have 4 because you have 2 of the same here. So this is going to be 3 different symbols. 1, 2, 3. We have an H, an S, and an O. Here you have 1. Here you have 1. 1, everything that's circled is going to be 1. So we can go in and say elements, you'll only see one of 1, 1, and then here we have to go in and count. We have aluminum, carbon, and nitrogen. So there's 3 there. Hydrogen and oxygen, there's 2. Nickel and iodine, 2. And sodium and chlorine, 2. So here are some questions. Does each compound have the same number of symbols? Well, I would simply say no. Not all of those numbers are the same. So for each element, those are the ones that are circled, how many total symbols are listed? Well, I just said 1. Okay, an element is by itself, it's pure, you will only see 1 symbol. What is the minimum number of symbols that must be present in order for a species to be considered a compound? Well, by definition, a compound is 2 or more elements. So we have to say the minimum would be 2. Some of them have 3. Okay, so that leads us to writing the definition for an element and a compound. An element only has 1 symbol. 1 symbol in its formula. Okay, and we call this a formula, a chemical formula. It's like the words in chemistry. Okay, and a compound will have 2 or more symbols in its formula. Okay, going on. So in order to understand compound formulas, we have to look at how we name them. So let's go to the next part, and it says within a compound you may see subscripts. Subscripts are the little numbers, sub meaning below. So the number will be below the symbol. The subscripts tell you the number of each type of atom that is present. So for example, if I say CO2, and I put the 2 down here, we have 1 carbon and 2 oxygen. If there are parentheses present around 2 or more atoms, the subscript applies to all atoms within the parentheses. So for instance, if I write aluminum cyanide, okay, and I'm going to write that for you, Al-C-N-3, okay, here's the parentheses, here's aluminum. We have 1 aluminum atom, and the parentheses tells you that you have 3 of everything that's inside those parentheses. So you'll have 3 carbon atoms and 3 nitrogen atoms. If one of the atoms within the parentheses has a subscript, then you're going to multiply the number by the number outside of the parentheses. So in order to understand this, you have to look at an example. So we have Fe2, SO4, 3. Okay, so, oh no, what do? I see all of these little subscripts here. It gets a little confusing. So this 3 on the outside of the parentheses is basically saying that you have 3 of these SO4s. So you'd have to kind of multiply it out to figure out. So you have 2 irons, and then 3 times 1 sulfur would mean that you have a total of 3 sulfurs. And you have 4 oxygens, but there are 3 O4s. So it would be 4 times 3 would give you 12. Now again, if I'm going too fast, you can pause and go back where I said oxygen, 4 of those times 3, because basically each of these parentheses means that there are 3 SO4s. And if you want to do it that way, you can to remember, but then you would say 4, 8, 12. 12 oxygens. 1, 2, 3 sulfurs. And then you have your 2 irons over here. Okay, so on the next page, it looks like it got cut off. Okay, so next page, common elements. You will be required to memorize the ones on this list for a quiz. So rules for writing element symbols. The first letter will always be capital. Okay? If I don't know what's going on with my pen here, guys. Let's see if I can erase this. Okay. So if there is a second letter, then it is lowercase. So let's just look at a few here. All right, we have the symbol for silver, AG. First letter is capital, second letter is a lowercase. Aluminum, capital A, lowercase l. Argon, capital A, lowercase r. So keep in mind, if there are 2 letters in the symbol, that second letter has to be a lowercase. Okay, otherwise you're kind of saying that there's 2 different elements there, and you have to watch out because some of them don't even exist. Like G is not a symbol for any element. Okay, so if you go through all of these, basically they're kind of starting with the first letter of the name of the element. Some of them are not, so they're tricky, and you would just have to memorize those. Okay, be prepared for a short quiz on symbols. Being able to name them from the symbol and symbol to name. Okay, I would say by Friday, September 20th. All right, so you should study those. Next up, all right, so let's talk about separation of matter. And there are several different types. The ones that we're going to talk about basically are all going to be physical means. And the first one is filtration. And what we do is we set up a beaker, a funnel with filter paper, and the solution that we have that's has particles in it that we can actually separate out physically through this process called filtration. So you're basically filtering it out. All right, so the description of the technique would be that you are taking the undissolved particles and they will remain in or on the filter paper, while the filtrate or the liquid passes through the filter paper into the beaker. That is one way to separate the bigger particles from a mixture. So what types of matter will this separate? This is basically going to separate heterogeneous mixtures. Okay, so for example, sand in water. Another technique would be through evaporation. Now there's two ways you can do this, either through using a watch glass or a crucible. Either way, both techniques are physical. And what happens here is we are separating the solute. And what is the solute? That is the dissolved solid. Okay, so we're separating the dissolved solid from the solvent, which is the liquid, in most cases water. Okay, so liquid. And how this happens is it's through boiling. So by boiling the solution. What happens is the solute escapes, and the only thing that is the downside to this is that you have very, very limited precision. All right, so a lot of the time you end up not getting all of the parts separated out. All right, so this would be useful for homogeneous mixtures, and we call those solutions when something is dissolved in a liquid or water in particular. All right. The last two, we're going to talk about distillation. All right, so this is how we get distilled water. Basically purifies the water. And this is another way of separating liquids by a boiling point. So again, this is a physical separation. And what happens here is we separate the solute from the solvent by boiling as well, another way. But what happens here is we recondense the boiled solution into a receiving flask to receive the recondensed material, receiving flask. And you end up with pure water here. Okay, so if you notice, boil the salt water, you will have a vapor then coming through this condenser tube, and that causes that vapor to recondense, turn back into a liquid through the tube and into the receiving flask, and you end up with pure water. Very useful for separating two or more liquids with different boiling points. And again, good for homogeneous mixtures, similar to the previous evaporation, okay? And let's look at the last one. Last one, chromatography. So chromatography is, again, a physical means of separating a mixture. And this basically separates particles by two ways. One, size, and two, solubility. And hopefully you remember what solubility is. We talked about that in lesson 1, how much of a substance will dissolve in about 100 milliliters of water. Okay, so this is a given, a constant for whatever substance that we're dealing with. And this is good for homogeneous matter or mixtures, however you want to say it. All right, so on the other hand here, chemical separation requires reacting a sample with something else in order to turn it into a completely different compound. Okay, so for instance, we have NaCl. Okay, in order to separate this, because it's a compound, it has to be chemically separated. So we would have to react this with like an acid, okay, in order to get this to come apart, for this to break apart. All right, so that concludes lesson number 2. Thank you guys, and enjoy working on your practice.